Okay. Okay. So we started by talking about a metal strap about 1 meter long. Heated by 500 degrees Celsius. It expands by 1 millimeter. Or more specifically, the length changes by 1 millimeter, right? It's an expansion. The reason for that is that molecules all need a little more elbow room when you heat them up and they get further apart because they're more active and they're more energetic. And that's a kind of a fuzzy thing. You really got to go to the quantum level to explain what's going on. Okay? And we're not going to go to that level. Anyhow, heated by 500 degrees, it expands by 1 millimeter. Okay? So, another, a bracket that's 15 centimeters long and 15 centimeters here. Length is 0.15 times as long as this, right? So there are only 0.15 times as many atomic spacings to increase by whatever. Of delta T, which is of course the 500 degrees in this case, or what? Well, the delta T is 500 degrees, which is one way to represent that change in temperature, or how not it's heated, and kind of using terminology carelessly, but delta T is 500 Celsius. Delta L, which is a change in length, would be 0.15 millimeters, right? So well, if it's heated by 200 Celsius, and you reason that out, okay? Now, if the length changes linearly with temperature, which isn't necessarily so, I'm going to start using the terminology. then your del L will be 200/500 of 1 millimeter. And that's 0.4 millimeters. Okay. Now, the way we want to really represent this, we're saying that if delta T is 500 degrees, we can say that L equals L naught times 1.001. Meaning, or same thing as the original length plus that 0.001 of the original length. And what 0.001? Well, because 1 millimeter out of a meter is 0.00, well, 1 millimeter is 0.001 of a meter. So it should be pretty obvious. You don't want to think about it. It's fairly basic. Okay. Now, what factor does the volume change? Well, the length will be your original length times 1.001. Let W be your width. And let H be your thickness. So your volume is going to be your original length, width, and height multiplied together times the cube of that 1.001. I'll digest that for a minute. Now, standard algebra topic is binomial theorem. Okay? At least it has always been regarded as standard topic. And it should be taught in high school algebra. But we are not teaching it in high school algebra because we're trying to teach high school algebra to people who can't learn high school algebra or won't learn it. So everybody sacrifices. Okay? Everybody who could learn it doesn't learn it. And doesn't have it when they get here, which is a handicap. Okay? I'm not going to tell you the binomial theorem. I'm going to put it. This way. Okay. Also, differentials. something you should have learned in calculus. But I find that people don't learn this in calculus. Even though there are a couple of problems that people are assigned and have to do, it's never really strongly tested. Or for one reason or another, maybe it's just hard to understand, but it's very simple. Okay? So you want to review both of those ideas. You want to get this one, high school level, and this one is something you should have learned in calculus. The way it works out is as x cubed prime equals 3x squared. There's your 3. And this, which is just an expression of the fact, if you follow the tangent line a little ways, you get from this point to this point, you stay pretty close to the curve. Now, all that you should be able to put together what you know from first year calculus. I can't teach you the calculus. But it's also relevant to multivariable calculus. You have differentials there too. So something you need to understand. If you're going to be able to apply calculus, one of the main things that you apply it for. I mean, there are many other really important things, but it's kind of a big deal. Okay. So both of these, and you can get into the relationship between this and this, but we're not going to get into that either. Okay. And we conclude that a 0.1% change in length implies a 0.3% change in volume. And if you follow it out for area, it's just L naught W naught without the H naught, you'd be squaring this because you only have one here and one here. You wouldn't have this one. And your area would increase by 0.2%. Now this works for small changes in length, and when you do expansion in a linear realm, you're going to get small changes in length. So this is something you kind of take to the bank. And well, the general rule then, and you notice that I hate to start with a formula, because if I start with a formula, people don't get past the formula. Don't bother understanding the formula, the reasons for the formula, and therefore fail to apply the formula as readily as people who understand what's going on before they see the formula. Okay, so we'll lock in the formula before you understand the topic, the concept. Okay, well, actually, enough to do the formula, you have to do one more topic. How much expansion do we have per unit length per degree? Okay. expansion per unit of length per degree, you divide your expansion by your length by your number of degrees. Expansion per unit of length per degree. Now this is going to be, well, going to be 0.001. You divide by 1,000 degrees, that'll be 0.0000001. That's going to be 0.0000002 per degree. Yeah, okay. We want to use this coefficient to find delta L for 7-meter rod. If delta T is 80 degrees. So can we do this? Okay. Okay, so okay. There's your calculation. It should be obvious why we calculate it that way, because this number is the expansion per unit of length per degree. Now, numbers are easy. You get 7 times 80 is 560. So that's going to be 1,020. So it's going to be 0.00102 meters. I wish you something so close to 0.001, but there it is. That's a bit more than the millimeter that we posited for a meter of the thing at 500 degrees. Well, 1 meter times 500 degrees is 500 meter degrees. 7 meters times 80 degrees is 560 meter degrees. Just a little bigger, right? And something's wrong about that. 560 times 2 gives me 1120, so it's 1.12. Number didn't seem right when I did that. You have a little more proportion. Proportional change in length than I said when I did that carelessly. Okay. Okay, well, now here's your equation, which you should totally understand without having to just memorize. Okay. This is because the change in length, well, if you multiply this, the 1 gives you your original length, right? And there's the equation. And then from what we just did, you can easily extend this to the equations for area expansion and volume expansion. Okay, I'm going to caution you that expansion is generally not completely linear. Your length versus temperature might well look something like this. Usually you don't have drifts and rises. It changes in concavity for most materials, but you can. Okay, and I'm not a material scientist. I don't know all the details of how materials behave. But the point is that this thing is not generally linear, but if we look at it over a small temperature range, it's very nearly linear over small intervals. And those small intervals might be a couple hundred degrees Celsius. Okay. So you got to take account of changes in linearity and use a little bit of mathematics to do that. So you see that these little segments are pretty close to the curve. Whereas if I try to expand to get the coefficient or the wavelength changes over this bigger interval from here to here, I'd have to cut from here to here, and I'd be missing the curve by quite a bit. Maybe it would be significant, maybe it wouldn't, depending what you're trying to do as an engineer. Okay. And let's say I fill this up. I said with mercury. Let's just say with water, because mercury is really heavy. I can't hold it. Okay. Fill this up with water, and then here's the whole thing, right? Water's going to expand. And water does not expand all that linearly. You can pick that up if you want. So I heat this up. You would think, okay, the water is going to expand, it's going to overflow, right? But you forget about the retainer, it's also going to expand. And the water either overflows or doesn't, depending which one expands more. Which one has the greater coefficient of expansion. That's something you want to be careful about, because you're going to see problems of that nature. Okay, something else I was going to say about that is the kernel of incredible wisdom, but I've lost it, so you've got to be deprived. Okay, for the general good, I'll clarify what this IE means. It means id s, and everybody knows Latin, so you know that means that is. IE means that is. EG means ergo goofball or something like that. I forget what the G means. But you know, I had a couple of years of Latin, but it's been a while. Not sure I ever really knew. Might be able to guess it. But EG means for example. This means that is. And maybe confuse this with multiplication. Now it's in a different box, but it's not multiplied, right? And we might as well just get rid of the parentheses, because you know you don't multiply by boxes. Okay? So that could be confusing. Okay, I don't know if anybody has a real fireplace. A lot of people have gas fireplaces. I used to have a real wood stove, but my wife made me get rid of it and smoke things up. If we were going to burn the house down, that was unrealistic. I look like somebody who burned the house down. Well, don't answer. Okay, so one of the biggest ripoffs I ever saw, attempted ripoffs of a yard sale. You know how you got pokers to poke in a wood fire, okay? Used to be standard implements in a lot of houses. They're usually made out of steel, some kind, okay? And if you leave them in there too long, of course, the heat conducts and can get your hand warm. So you want that poker to not get too hot at this end if that ends in the fire. So you design it accordingly. And you usually make it out of steel. This guy had solid gold fireplace instrument. We wanted $50 for him. No idiot is going to use a solid gold fireplace poker, because gold has a high thermal conductivity. It's going to burn your hand. So the guy's an idiot, you know. Nobody's going to give you $50 or something like that. Then I got to thinking about it. Wait a minute, gold's worth some money. You know? And then somebody had already bought them. Okay, well, that's something I made up, obviously. I don't know if anybody makes solid gold fireplace pokers. If they do, they're mostly for So they're also over twice as heavy as steel. Okay. And not as strong. Okay, heat conduction. Just think of a bar, or if you like, a wall, where this side is at one temperature, and this side is a temperature I'll call T sub F. I don't know what that notation I'll use. Same thing here. We got T naught here. We got T sub F here. Okay, now T sub F is greater than T naught, then heat is going to flow this way. If TF is less than T naught, then heat is going to flow this way. Okay. Make sense? I mean, that's your experience. Trying to heat your house. We've had a reasonably cold January. If you're trying to heat your house, you want as little heat flow through the wall as possible, right? Okay. Looking for the symbols we use. Different types use different symbols. Okay. So heat flows from less or greater temperature. And the rate of heat flow in either of these cases is some constant times the area, cross-sectional area, because if you got more cross-sectional area, you got more area for the heat to flow through, right? Okay, so you got a greater cross-sectional area, but what about the length? What happens in terms of the length? If you increase the length, is that going to increase the heat flow or decrease the heat flow? Or if you increase the thickness of the wall? Intuitively, that's going to decrease the heat flow. Okay, well, we're going to divide by the length, where this is the length. And then the other thing is your delta T. Now, notice if TF is less than T naught, then this is going to be negative, right? So if you think that the positive direction is from T naught to TF, then a negative result means temperature is flowing this way, right? And so positive direction is from T naught to TF. With that convention, there it is. Okay, more generally, since we're all masters of multivariable calculus, A times the gradient of T. Over the length. So T could be a complicated function of three variables within some material that has different temperatures at different points. If you have your temperature function, just take the gradient, apply that at a point, and you find the temperature flow at that point. Okay? So there's a little bit of difference here. Well, I'm just going to leave it at that. You do the gradient. We'll still talk a little bit more about that later. I don't want to get into that. But this TF minus T naught and actually when I did the temperature gradient is with respect to the length. I didn't quite write that down correctly, but this is KA times the space gradient of your temperature function. In other words, this TF minus T naught over L is a one-dimensional version of a more general gradient. So the temperature gradient is the rate at which temperature is changing per unit of length. So it's the rate of change of temperature with respect to length. This rate is the rate of heat flow with respect to time. All this can be expressed a little more rigorously in terms of differentials and multivariable calculus. But we're not assuming multivariable calculus for this course. I'm not going to say too much more about that. Relate this to what you know about multivariable calculus if you know multivariable calculus. That gives you a bit of an entry into some more general and more sophisticated models. Okay. So you can read the examples. The idea is pretty simple. The more rapidly heat changes as you move across something, the bigger the temperature difference between here and here, let's say, the faster heat is going to flow between here and here. It applies, of course, over the entire length. And can be integrated and all that stuff if you have an irregular object, and not going to talk about that. Okay. But just because we're moving through this part of the course relatively rapidly. Okay, well, that's one method of heat transfer. This is heat transfer by conduction. Heat is conducted through material. Heat transfer by radiation. The rate equals E sigma area times T to the fourth. E is called emissivity. Sigma is the constant, the universal constant. Okay. Stefan Boltzmann constant, which surprisingly in a early graduate level course in electromagnetism, I found could be derived. I had a problem, I had to derive it by considering a gas consisting of photons within a perfectly reflecting cylinder. Really neat, kind of really neat revelation. Took me a little while to get it, not too long. It was just a total change of concept of what you do with thermodynamics. Okay, which I don't know all that much about, but still. Okay, area. Is A. T is the temperature of the surface. The radiation is just like light. And light is a form of radiation. Sun emits energy, emits surface. Surface is about 6,000 degrees Celsius, so T would be 6,000 degrees Celsius. Area of the surface, basically the area of a sphere of radius almost a million, of diameter almost a million miles, okay? Which is like radius of 800,000 kilometers or something like that. Sigma is sometimes 10 to the negative 8 with the appropriate units per unit of area per Kelvin to the fourth, okay? And I'm a little bit consternated because I don't remember what that constant is. Which is pretty bizarre. Starting to forget constants. Oh, I'm getting older. What's the number? Times 10 to the negative 8. I don't remember. But yeah, you'll see it. Okay. E is emissivity. Okay. If this surface is hot, being black, it absorbs radiation that comes into it and it emits radiation easily. Okay? That's something that can't heat up all that much. If this was a reflecting surface, its emissivity would be, as a perfect reflector, its emissivity would be low, like 0. Okay? It wouldn't emit. It reflects all the radiation that comes into it from outside, and it reflects all the radiation that comes from the inside to the out. Okay? So radiation can't get in or out. By radiation, I don't mean radioactive elements, I mean like light, or infrared, okay, or ultraviolet. You'll see something about the way radiation has occurred with something like this. So where this is the amount of energy, the relative amount of energy, and these are wavelengths here. Don't, you know, a lot of times I can't say too much about that. You're going to have to read about it. I don't think you have problems that are that big, you know, that require that much with this, at least in the assignment I've given you. I'd like to go deeper into it, but, you know, we got a lot of limitations of time. So we have this, so I'm going to kind of erase it. Use 0 for perfect reflector. And E equals 1. Also equals perfect radiator. What we refer to as a perfect black body. People, human skin is pretty close to a perfect radiator, and it doesn't depend on pigmentation very much. Okay, the lighter skinned person, the darker skinned person, pretty much absorb all the radiation that hits them. which is an advantage if you're trying to stay warm on a sunny day. It's a disadvantage if it's too warm on a sunny day. Okay. So if it's too warm on a sunny day, hopefully you sweat a lot, so you lose heat to evaporation. We'll talk about how that works later. Make sense? Somewhat? Very simple equation. The thing you got to remember is now, if I'm outside and the sun is hitting my skin, I'm absorbing radiation from the sun, which will warm me up. I'm also radiating away toward the sun. Okay? So you got to take my temperature and consider the temperature of the sun when you figure out what the net radiation is. That turns out I'm not radiating much. Okay? If I'm in this room, then my skin is at one temperature, the room is at another temperature. It's a real warm room, the temperature of the room might be greater than the temperature of my skin, especially my hands, radiating with a lot of heat. Okay? So that I have radiation coming in from the room, and of course, radiation going from my skin to the room. Now, unlike the sun, which is at 600 Celsius, and my skin, which is probably around 30 Celsius, so the T to the fourth overwhelmingly favors the sun. Fourth power of 6,000 is way, way bigger than the fourth power. Of course, it's got to be absolute temperature. Okay, so 6,000 Celsius is pretty much 6,000 Kelvin. My temperature is 273 plus 37, about 300 Celsius, 300 Kelvin, absolute temperature. So 300 to the fourth is a pretty big number, but 6,000 to the fourth is a much bigger number. Okay. I don't radiate much heat away to the sun. In this room, where there are only a few degrees difference one way or the other, then the amounts of radiation are fairly comparable, and you're looking at the difference in the radiation that comes away from my hand and into my hand to see how much net radiation there is in my hand. Okay? If you're outside on a cold night, then your skin is, let's say, at 30 Celsius. On a cold night, it might be a little warmer than that, but around 300 Kelvin. Then you look up, you're facing outer space, which is pretty much close to absolute zero. Okay? So you're not getting anything much from outer space, but you're radiating away toward outer space. Okay? So you lose a lot of heat. That's what a crisp, clear night feels like. You lose a lot of heat. Feels kind of good if you're dressed for it. If it's a cloudy night, then it's between you and the clouds, which are not nearly as cold as outer space. You're at 300, the clouds might be at 200. So you look at the difference between 300 to the fourth and 200 to the fourth Kelvin. Okay? Make sense? I think that's the Stefan Boltzmann constant. I think Stefan Boltzmann constant 1.38. Sometimes 10 to the negative 23rd per particle Kelvin. I'm losing track of what the names of these things are, but anyhow, that's a universal constant, it's got a name. Okay. And Stefan is in there somewhere. And I don't think Boltzmann is. Maybe I should have taken a glance at the book to have the names and stuff. And the constants, I can't believe I forgot a constant. Okay. So there's your introduction. You get a lot more from Pearson materials if you can ever get in.